Greetings. My name is Julius Smith. I'm the last speaker today and wanted to talk about physical modeling in Faust. Start with a overview of models and the types of models we use, and then get into some examples. And I will build on the previous talks by focusing on what they did not focus on. So what is a model? You can think of a model as any form of computation that predicts the state at some future time of a physical object or phenomenon based on its initial state and any input forces through time up to the present time. And so this is diagrammed here. So we've got some object and we're driving it with a force, and we want to calculate what state it will have at time t. And then we have this notion of outputs of a system or of a physical model, and that would be some function of the state as well. So the purpose of the state is to summarize everything that matters about the object's behavior. It's the state of motion, its position, velocity, acceleration. In the case of electrical entities, it would be voltage and current. It's what you need to know to uniquely specify the state of the object, as opposed to its materials. So its materials would be fixed constant parameters such as masses and spring constants, capacitance, inductance. Those are fixed parameters of the system. The state is what changes naturally in normal operation, and that's what we need to simulate when we're simulating a system, when we're modeling a system, and when we're predicting its behavior, predicting its state through time. And so we only have forces coming in, but you can also effectively drive with other things. But ultimately it's forces. Even if it's a current source, you can think of a current source as a force through a very, very large resistor that will force a certain current. That's the way it happens in reality. So forces are general enough. There's only 4 of them, and that's all we have. So we will use vectors so that we have any number of forces. And for our world, the object is a musical instrument or an audio effect, like a circuit that emulates some effect that we like. And then we'll have the state, and that's also a vector. So there'll be some number of state variables that specify the state of the system. And then we'll form an output from the state somehow. And why do we want to do this? When do we want a physical model as opposed to just a recording, sampling, FM synthesis, additive synthesis? There are a lot of synthesis techniques. Why do physical modeling? Well, it's really nice when you want a lot of dimensions of expressive control. Now, it's easy to do that in general, in the abstract, because you can have any number of dimensions of any function. But when you have a lot of dimensions, you want to understand them. And physical models you can think of them as multidimensional expressions, formulations that we have lived with all of our lives. In other words, we lived in the physical world. We've played real instruments. We understand those dimensions. We know what it means to play a piano harder, to move a plectrum up and down a string. So these become very predictable. And when you have a lot of dimensions, the predictability is really valuable. And so the multidimensional expressive control is especially valuable for performing musicians. The listeners don't really hear it. They don't know what you're going through up there. The audience members just hear the final music played, so they really don't know what the performer could have done or how constrained the performer may be. And so the performer can carve out a particular performance subspace of this high dimensional space and deliver a very unique and expressive performance, and one of a huge possible space of performances that are not available in a sample context. Well, it's not impossible in principle with sampling. You just have to do a lot of recording. Just think of how many recordings you have to make to capture a violin at every imaginable velocity, bow position, bow force, all the variable controls that you have, everything that can happen on the left hand. You have to sample every possible dimension densely enough that you can interpolate those recordings, and that's a lot of work. So if you have a model, it becomes a very small footprint, and you have all the natural expression, reaction to your performance, and it can run in real time. So we're lucky that we don't need advanced physics. We just need Newton's law, F equals ma. That's force equals mass times acceleration. That's really it. We don't need quantum mechanics. We don't need relativity. It's the most elementary starting point of physics. Isaac Newton started it out. And it's an ordinary differential equation. That's just a fancy way of saying that, the force equals the mass times the second derivative of position with respect to time, or the first derivative of velocity with respect to time. So there's a little calculus involved, but it's a very elementary equation. It's a first order differential equation in velocity. It's a second order differential equation in position. And it's an ordinary differential equation in that we only differentiate with respect to time. But when we talk about strings and membranes and spaces, then we have multiple derivatives. We have derivatives with respect to spatial dimensions, and that's when we call it partial differential equations. So it's still Newton's law, but we end up doing it in space as well as across time. So there's ordinary and partial differential equations, and that's really where it all begins. It's Newton's law, and then you use Newton's law to formulate your differential equations. And then we digitize those somehow. Because we have to implement everything on a computer nowadays, and so we will form difference equations, or finite difference schemes. So we'll find some way to essentially numerically integrate our differential equations through time in order to execute the behavior of the model. And so the forces will come in, and the differential equations will tell us what the system does, and then we'll extract an output, and that's our physical model output. So even though this is a very simple equation, in the scheme of things, you can get very complicated very quickly when you combine a lot of them. When you have this is only one mass, okay? So when you have a lot of masses and they're interconnected by springs or other kinds of linkages, then you will have a very complicated situation very quickly. And so it opens the way for a lot of simplification approaches. There are a lot of interesting techniques that have been developed to tame the computational complexity in these various situations. So I thought I'd talk a little bit about the history, and I'm borrowing a very nice figure from Stefan Bilbao's book, Numerical Sound Synthesis, and it's a nice summary of the history of sound synthesis and physical modeling. And so the physical modeling is down here at the bottom, and that's what I'm going to talk about. And so, as I said, it started with Newton's law way back here, and then computers came along in the 1950s, and we had to discretize them or digitize them. And so we got into difference equations, and that's like a special case of finite difference methods. There are many, many kinds of finite difference schemes. Just think of how many differential equations there are, and imagine having 10 different ways to digitize them, 10 different finite difference schemes for each type of differential equation. It gets to a large number of things, and there's all kinds of methods for analyzing their relative merits. So here is where it forks off into one of the talks you've heard. So the mass interaction library comes from Claude Cadeau's in Grenoble, his work with the Cordes Anima system. And so that's a very early physical modeling system. It's in the category of finite difference approaches. And another very early example is Pierre Ruiz working with Lahar and Hiller on applying finite difference schemes to bowed strings. And that was one of the things I cut my teeth on as a graduate student. I read that and was very interested in it. And it has progressed through time. Antoine Chen did much for the piano, guitar. And then there's just an enormous number of things going on out here in the form of finite difference methods for simulating physical systems. Very, very general. You can take any set of differential equations and numerically integrate them in some way. Another connection actually is wave digital filters, which you heard about earlier today from Dirk. The wave digital filter approach came along in the 1970s. Alfred Fettweis, it was the originator. and he was very influenced by Belovitch, who did a great treatise on classical network theory, which just incidentally is where digital waveguides came from. I was studying Belovitch when the idea for digital waveguide networks was born, and it was for reverberation, not synthesis, but it's just a very fertile book, this classical network theory book. And I believe that Fettweis actually worked with Belovitch. In any case, wave digital filters is from Alfred Fettweis, and it's a scattering formulation of analog circuits such as RLC, resistor, capacitor, inductor. Those are normally done as lump systems with just voltage and current, but you can also express the voltage and current as traveling voltage waves and current waves, and then you get the wave digital filter paradigm. And it's got excellent numerical advantages, and it's been used extensively for circuit modeling, and it's still one of the very best ways to go for modeling a circuit. And so now you've seen how that maps into Faust. And so you can see some of the cross connections here. Wave digital filters were also studied as an approach for general differential equation solving. That's back there in the literature. And so so that's a very rich vein as well. Now, the very earliest digital synthesizer that I know that actually was used to synthesize sound digitally, for in a physical modeling way was the Kelly-Lochbaum vocal synthesis technique, and it's basically a transmission line model for the vocal tract. And Max Matthews, the father of computer music, did the musical accompaniment in the very first demo that we know of by the Kelly and Lochbaum method, and I have that on my website. I have it in other talks, and you can find it and play it and hear it. And they were working towards speech synthesis. So this was work at Bell Labs, and Max Matthews was director there. And they did an amazing demo of speech in the 1961 timeframe. And so that research actually seemed to sort of go in pause for quite a while, but then it revived in later years. Perry Cook gave it a big shot in the arm with his thesis on using this approach to essentially as a singing voice technique. I came up with digital waveguides, as I mentioned, based on Belovitch, but sort of in retrospect, realized that it could have also have been discovered as an extension of the Kelly-Lochbaum approach, because all you have to do is erase a lot of the scattering junctions in the Kelly-Lochbaum formulation, and you'll get digital waveguides out of it. So in both cases, you have scattering. But what the Kelly-Lochbaum doesn't have delay lines. It just uses single sample delays. And another thing you can derive as a special case in retrospect is the Karplus-Strong algorithm. And so that's here. And so all these things, connect together. There's a lot of independent reinvention going on, and a lot of connection going on. But when it all comes down to it, it's Newton's law. This approach up here in also wave digital filters is based on a wave formulation, and you do go from Newton's law to waves, but you have to formulate the wave equation for the string, and then you have to solve it to get the traveling waves, and that was done by D'Alembert in I believe it was right before Bach died. So it's way back there as well, and so there are ways you can describe it as arising from that and coming out this way. So we have two main formulations, sort of the lumped formulation involving masses and springs, and you do finite difference schemes based on that. And then you have the wave-based approaches, and that's the Kelly-Lochbaum, Karplus-Strong. Well, Karplus-Strong was not a physical modeling approach, but it was interpreted that way, years after it came out. It was interpreted physically as a transfer function approach at the time, but that once again things connect in retrospect. So here's and then wave digital filters is a wave-based approach, and it's a very interesting case of a wave scattering formulation of a lumped system. So it's essentially a wave environment where the speed of wave propagation is infinity, which is very unusual. But it's got wonderful properties because of the scattering formulation. It ends up having excellent numerical properties, for example. So then up here we get to Max Matthews starting computer music, and it started out with wavetable synthesis, which is just a small, one period in memory that gets read out over and over again at different rates to get different pitches. And so this goes into other synthesis traditions that I will not get into, except I will talk a bit about modal synthesis, because modal synthesis can be derived as a physical modeling approach. So if you have a physical system and it's got resonant modes, then it will spontaneously decompose into a sum of resonators, and that's what you have in modal synthesis. And the only real difference between how it was practiced originally as a synthesis technique and coming from physical modeling is that you know how to drive the modes, and you know how to combine the modes to reproduce a particular physical scenario. So like if you move your drums around, move your sticks around on a drum, you get different mode excitations. And if you put your pickup at different locations on a drum head, you'll get different combinations of modes. And that's what all comes out automatically when you formulate it as a physical model and then convert it into a modal synthesis. And I'm going to talk a little bit about that today. And then if you let the damping go to 0, in the modal synthesis, you'll get additive synthesis. You'll just get a sum of sine waves, and these things all interconnect, and I could go on, but I'll try to stick to where I should be here. That was some history. So here are the formulations that I know about. There are probably more out there, but I already mentioned ordinary differential equations. You differentiate with respect to time. Partial differential equations, you have derivatives with respect to time and space, 1, 2, or 3 dimensions. Although we can go to more dimensions if you want to hear things in 10-dimensional space, why not? And then if you digitize them, you get what you could call difference equations, but the more general name is finite-difference schemes. And I would say difference equations are when you directly digitize differential equations by some simple, substitution, like first order difference for a derivative, that kind of thing. But finite difference schemes go much beyond that. In other words, like just look at fourth order Runge Kutta to get an example of things that are not just a simple substitution for a derivative. And I already mentioned transfer function modeling. So if you know the physical input to a system and the output, and it's a linear time invariant system, then you can get its transfer function. And that's how I was modeling strings during my thesis years. You would excite a string, and its transfer function was known. It's e to the st, where t is the delay. And so that was the transfer function approach. And it's also very common in classical control theory. So classical control is based on transfer functions models of what they call the plant. So the system is always called the plant. And in our case, the plant would be a string or a bore of a woodwind. And so transfer function models were big. They were used extensively. But at some point, the control systems reformulated as state-space models somewhere around the 1960s, around the time of the Kalman filter. The aerospace program was adopting them. They were using them for satellite tracking, that sort of thing. And so state space became the standard formulation for control systems. And so that's when they started calling this old transfer function modeling approach classical control. So you had classical control and what we do now. And state space models are still really big. In particular, they're really big in the MATLAB world. And there's a whole story there about how MATLAB was originally developed by Cleve Moeller at University of New Mexico, and he just wrote it as a desk calculator front end to his numerical linear algebra libraries, things like IcePack and LinPack. These were subroutine libraries in Fortran for calculating eigenvalues and linear least squares solutions. And so it was a really neat language for running experiments. It had no files, had no functions. It was really a nice little interactive desk calculator interface to the subroutine library. And then a number of people picked up on it and took it much further. And I worked at one of those places, Controls Systems in Palo Alto. And Control C was the name of the competitor at Integrated Systems. So there were a lot of people working on this. So our company was Systems Control Technology, and we were working on what was MATLAB for control systems, and that's the reason it's probably the dominant component of MATLAB today. I haven't checked that out, but every time I've checked, it's been the dominant library space, and that's important to know because it means that the state space approach is perhaps the most supported approach in terms of computational support from systems like MATLAB. Now, if you take a state space model, it tends to be a little expensive. It can be, although Jan Orlari did some interesting benchmarks that showed that for the cases we tried, such as a biquad filter, the state space model was about the same as just a normal direct biquad implementation with using direct form 2, the standard things that are in the libraries. So that's because these are sparse matrices and the compiler is good at optimizing and not computing anything unnecessary, so that you can hope that your state space model will run at the same speed as your ordinary transfer function model. But that doesn't normally happen without some good optimization going on, because your state space matrices are order n squared, where n is the order of your system, whereas your transfer functions have coefficient order n set of coefficients. So you have to be careful to not spend more time doing the computation. But what people very often do to guarantee that that's not a problem is that they diagonalize the system. So there's a thing called a similarity transform. You get the matrix of eigenvectors of the state transition matrix, and that gives you a transformation matrix that will then take you to modal coordinates, where all the modes are vibrating on their own axis, so to speak, in the space, and then it's a diagonalized system, and everything's in parallel, so it's a set of one-pole systems in parallel. But unfortunately, the poles can be complex, so what we do is we combine the complex poles to get biquads. So you make a parallel bank of biquads, and that's what we usually call the modal representation. It's just a set of parallel second order filters, or first order and second order. And so that's a very common final form of a state space model. And then some other representations that are used a lot are equivalent circuits. You'll maybe take, let's say, like there's a really classic paper on the violin as a circuit by Schelling. It's something that was done a lot, a century ago. And you would just take a physical system or an acoustic system and come up with the equivalent circuit for it. You can find equivalent circuits for the ear in various, the basilar membrane of the ear, the way hearing works. So there are all sorts of circuits out there, and so it's nice to be able to digitize those. And a good way to digitize a lot of systems is to first get the equivalent circuit and then digitize that circuit, because there are very nice systematic methods for digitizing circuits, specifically things like the wave digital filter digitization of circuits. Impedance networks are also valuable, and probably don't have time to get into them, but I just wanted to put it down here because I think it's an important representation, and it's used for circuit analysis. So once you have your equivalent circuit, you can now replace every element in the circuit by its impedance. And if it's a linear time invariant circuit, you can do very elementary resistor analysis of the network, because you can manipulate the complex impedances of things like inductors and capacitors as if they were resistors when you're in this this impedance space. It's like taking the Laplace transform of everything, and in the differential equation space, it turns the differential equation into an algebraic equation. So your ordinary differential equation just becomes a polynomial in S for the analog case, continuous time, and it becomes a polynomial in Z for discrete time, and those are a lot easier to work with. And then there's wave digital filters and digital waveguides. All right, so those are the main formulations, I would say. Okay, so let's talk a little bit about state space models. We can start with the equations of motion for some physical system, and then formulate it in a state space form where we have the state x, which is a vector, is combined with input forces to give us the derivative of the state. And that means it tells us where the state is going. And then you can integrate the state derivative to get what the state's doing. So this is, you can think of it as kind of like a generalized mass. It's like a vectorized mass. Because this is the way a mass behaves. You apply a force to a mass, and F equals ma. So you can see that the force divided by the mass gives you the acceleration, and then you can integrate the acceleration to get the velocity. So if we choose the state variable to be velocity of the mass, and the input is a force, then the acceleration comes out, and we integrate it to get the velocity, and then we are therefore choosing our state variable to be the velocity. But the point I'm making now is that this is very, very general. This is by vectorizing the state variables and the inputs and the force inputs, we're representing an arbitrarily large system. You can even model the brain in this form as a state machine. About the only thing we've really conceded here is that we're assuming causality, and that's just life in the world, right? You can't predict the future, so this is extremely general, but it is constrained to not be able to predict its future inputs, and so the future behavior of the system can only be a function of its current state and its current inputs, and anything about the past inputs is summarized in the state. So the state is a sufficient statistic, so to speak, for the entire history of inputs. So all we need is the input now and the state now in order to predict the system for all time, if there were no further inputs. But there'll be more inputs, and so we'll need those. Okay, when defining a state space model, you want to choose states that provide a physical amplitude for some energy storing degree of freedom. As an example, for a mass, you would not pick the velocity and the position, even though those are very important. You would think of those as being necessary to specify the state, but the position does not store energy, only the velocity. So the kinetic energy of a mass is 1/2 mv squared, where v is the velocity. For position to correspond to energy storage, there would have to be a spring involved, and we associate that energy with a spring. So you would have position and velocity as state variables in a mass spring system. So just think of a state variable as the physical amplitude for an energy storing degree of freedom, such as the displacement of a spring or the velocity of a mass. And you get one state variable for each energy storage element, each spring, each mass. And notice these are what we call lumped elements, as opposed to distributed elements such as vibrating strings, which you can think of as a continuum of masses. It's an infinite number of masses in principle. It's the limit of a mass spring chain, in the limit as the masses go to zero and the springs go to zero very close together. So in a circuit, in an RLC circuit, you get a state variable for each capacitor and for each inductor. I can't highlight, there it goes. And so then when you discretize, you'll have a state variable for each units of delay. So every sample of delay is an energy storage element. It holds one sample, and its energy is proportional to the square of that sample. That's the energy in one sample, the power, you could say. And the actual units matter, so it's usually the square of the sample divided by the impedance that it's in, if it's a force or a voltage, that sort of thing. Okay, and then the number of state variables is the order of your system. It's the order of the polynomials. Transfer function, if you look at the transfer function, and it's the order of the matrix, the state transition matrix in the state space model. So that's just a summary of state variables. And now you can get the modal representation from the state space representation. Let's just jump to that real quick. So let's say we have a linear state space model like this. We can diagonalize it. So all we need to do is find the eigenvalues of the state transition matrix. And eigenvalues solve this equation, that the matrix times the eigenvector. The matrix times the eigenvector is the eigenvalue lambda sub I times the eigenvector e sub I. And so if your poles are distinct, if the eigenvalues are distinct, then you'll have a set of linearly independent eigenvectors, and you can form the similarity matrix, the transformation matrix. So you just put all the eigenvectors side by side in a matrix, E, and that is your transformation matrix. And if you don't have distinct eigenvalues, then there are things you can do. You use generalized eigenvectors, and it works out. And you can look that up. In MATLAB, you've got you've got the eig function for finding the eigenvectors and eigenvalues, and you can use that to diagonalize the system. So you're essentially changing coordinates. So this is our original state vector, and we define it as the matrix E times a new state vector, which is in modal coordinates corresponding to the diagonal system. And so we have an identical state space system in form, but we have transformed to a new set of coordinates, which are the modal coordinates, and the new matrices are given by these formulas. So there's no change to the feed around term, but you have a new C matrix and a new B matrix and a new A matrix. And this is called a similarity transform, and it does not change the eigenvalues. It's the same system, but it's been it's gone through a change of coordinates. It's called a similarity transform. And so the transfer function of this system is exactly the same. But the big advantage is this is a diagonal matrix. You've diagonalized the matrix, and it follows directly from the this equation right here. You can use that to show that this matrix diagonalizes the system. Very quick derivation. And so if it's diagonalized, it's more efficient. You can implement your system as a bank of complex one-pole filters, and you can group the complex conjugates one-poles together and make biquads out of them. So you can have a parallel bank of biquads, and if they're real poles, you can just leave them as one-pole filters. So that's usually what you do if you're really using state spaces, diagonalize it. Now that also requires linear time invariance. These transformations are not so easy if you have a system that's changing. If it's a nonlinear system and your elements are varying, then you would want to do all this in closed form. You have to keep track of everything. So we normally only do this for linear time invariant systems, or at least linear. We don't want to be doing closed form operations for matrix elements that might change. Okay, so that's the modal description right there. And on this MATLAB page, it shows you an example of modal canonical form. So this is for the continuous time case, which is looks the same in most ways. So here's the eigenvalues. So you have two real eigenvalues and then a complex conjugate pair of eigenvalues. And in the discrete time case, that would be e to the plus or minus j omega t times r. R would be the coefficient corresponding to the damping sigma. And then the real case is just real. And then here's you can see the there's a real eigenvalue here, a real one there, and this little 2 by 2 block is the biquad. And it came out looking like this. But this can be any little 2 by 2 state space matrix. What we saw was minus A1, minus A2, and 0 and 1 on the bottom. So it's whatever you want there. There are a lot of different forms there. It depends whether you started with direct form 1, direct form 2, normalized, lat. There are all these different forms. You can get a lot of different things here. But whatever it is, it pulls out now as a separate subsystem. So you can now implement this as 2 parallel one-pole filters and a parallel biquad. And the B matrix and the C matrix will change as a function of how you choose this form in the biquad stage. But whatever it is, you just pluck it out and implement it separately. So that's usually what you really do. So now we're ready for the example. All right, let's take a look at state space modeling in Faust. All the other approaches except state space and modal synthesis have been covered in other talks. So I'm just going to do state space, and then, as I mentioned, if I diagonalize the state space model, I've got a modal model. So the digital state space model is written like this. So Y is a vector output, it's just any number of outputs, is some C matrix times the state vector, X underbar, plus D times the input signal. And the D is direct. It goes around the system, actually. So Y is getting a direct feed from the input that bypasses the state completely. And now the state update is here. This is for the discrete time case. I showed the continuous time case where you get a derivative as the output, and then you have to integrate that to get the next state. Here we just jump one sample forward and calculate that. So you can think of this as having numerically integrated derivative for one sampling interval. So the state at time n+1 is the state transition matrix A times the current state plus the B matrix times the inputs U. And here's everything all written out. And so I'll just say we have capital N states. That's the order of our system. It would be the number of poles and the transfer function of the system. And then we have any number of inputs P and any number of outputs Q. And so that forces all these matrices to have these sizes. We can observe that the matrices B, C, and D are feed-forward matrices from the input to the output. And the A matrix is a feedback matrix. Everything else is feed-forward. A is feedback. And a really important point here is that all 4 of these matrices can change every sample. So this is a very general implementation of time-varying linear systems. We're still constrained to linear because of this structure here. So the output is a linear combination of state variables plus a linear combination of inputs, and the state update is a linear combination of the current state plus a linear combination of inputs. So we're staying within the space of linear systems, but it can change every time instant. We're also staying within the realm of causal systems. So we still have no ability to predict the future here. So we're dealing with linear, time-varying causal systems of any type. Okay, so here's some Faust code that will do this. Let me go into this mode. So we're going to have 2 inputs, 3 outputs, and 5 state variables. So it's a 5th-order system. And I will put this code in the comments down below, so or a link to it, so you can download it and try it if you want. So we have 2 inputs, 3 outputs, and 5 state variables. And so I've defined a little function down below that will define a matrix. So this is an n by n matrix, and then we have all these other matrices, their various sizes, and here are the definitions of those. Here's the definition of matrix. You can take a look at that. It's not unlike the example in the Faust distribution that's already there. And these are there's one little detail here that you need to delay the B matrix in order to get the standard definition of state space and discrete time. And I'll show you on the figure, the block diagram. It's easier to see it there. And so we define this vector sum here as a bus that then interleaves down to a bus of length n, and that will sum two n vectors for us. And here's an impulse that we'll use for setting the initial conditions. We want to be able to have an arbitrary initial state. Usually a state space system will allow you to specify an arbitrary initial state, and then everything after that is just the inputs coming in. So here's our initial state. It's we're just arbitrarily setting it to 0 through capital N minus 1, and the impulse, make sure it only happens at time 0. This is just for the example. But you would put, instead of I, you would put whatever your actual initial state variables are here. And then here's our system. So whenever I'm writing Faust, I always like to fix the number of inputs and fix the number of outputs. So I start with a bus of size P because I want P inputs and nothing else. And for the outputs, I want Q outputs. And so then we'll fan out to the D matrix, which is going to go up and over directly to the output. And then we have our this is what I would say is the real heart of the state space system, where we come in through the delayed B matrix and go into a vector summer with the state, and then that feeds back around through the A matrix, the state transition matrix. And then on this other parallel branch, we have our initial conditions going into a vector sum with the C matrix multiplication, and then all that fans down to the outputs, Q outputs. And so process equals system. So let's take a look at the diagram for that. That's funny. The mode changes when you're in this mode. All right, so here's the state space model. 2 inputs, 3 outputs, and 5 state variables. 2 inputs. Here's our delayed B matrix. See, the reason this is necessary is because these delays introduced by feedback do not affect the feed-forward path. And so we have to put it here. What I'd like to do is just push these delays into this branch, and then I could use a normal B matrix here. It's just a matter of definition. That's all it is. So the state initial condition comes in here, and it fires at time 0. Remember, it's got those impulses multiplying it. It's multiplied by an impulse, you could say. So it only fires at time 0 and goes into the C matrix at time 0. And then this delayed B matrix holds off the input for time 0 because it should not affect the output at time 0. Anything that affects the output at time 0 from the input goes this way. Okay, so the D matrix takes care of any direct bypassing the state dynamics part. All right, so here's our B matrix. It comes in. So this is your state. So these delay elements contain the state variables, and the A matrix feeds back around, and then you sum. So this is x of n plus 1 summing with B times U, the input, and that forms the next state. And then the C matrix takes a linear combination of the states and puts it out. On the first sample, time 0, it's C times x0 that goes out. That's your, time 0 output. You also add D times U to that. So time 0 is very different from everything else. It's x0 plus B plus U, D times U. And then after that, you're looking at the input through B, and the output is C times the feedback. I want to tell. I'm about to say the transfer function, but I guess I could say C times SI minus A inverse, or ZI minus A inverse times B, but that's not fair because I haven't derived that for you. But you can see right here what it's doing. Let's go back to this mode. There we go. All right, so to use this, we have to get these state space matrices. How do we get our A, B, C, D matrices? And it's actually very straightforward. What you do, let me jump to an example here. This is a biquad in direct form 2. This is a basic direct form 2 digital filter order 2. So you just write it down any way you want. So you just write down any block diagram, and then you go find your delay elements, and those are your state variables. Every delay element contributes a state variable. Now, if you have a delay line where there's nothing going on, let's say I didn't have these lines and it was just a delay line, you can handle those as one unit. And if you've ever looked at feedback delay networks, then you've seen this before. Feedback delay networks are essentially written in state space form. They're analyzed in state space form where you have generalized delays of any size. So in normal state space, these Z inverses are always Z inverse, but in a feedback delay network, they can have arbitrary size. And that's used a lot in the reverberation world. So, but you can also just go ahead and label every single element of the delay line, and that would be the strict state space model. And so that's what we have here. And so you go just arbitrarily number them. You know, I could interchange 1 and 2 here. It doesn't matter. That's why it's not unique. But if you tend to be systematic, you'll tend to get about the same thing. And so these are our state variables. And now you're ready to write down the state space matrices. So think about X1. All right. What do we need? We need to know the state update. So we write X1. So we're looking at the state update. So we want to write X1 of n plus 1 as some linear combination of the input and the state variables. And we know that's possible because by definition, the state summarizes the system at time n. And so the only thing X1 of n plus 1 can possibly depend on are the state variables and the input. And so we just figure out what that is. And so you see that X1 of n times n plus X1 of n plus 1 is going to multiply U of n times 1. And it's going to multiply X1, the previous value, by minus A1. And we're also going to have minus A2 times A2. So we can see that down here. So B, the first element of the B matrix is 1, and that's this path right here. And the top row of the A matrix is minus A1 minus A2. And so you see that. So you can just read it right off the block diagram. You just trace the lines in the diagram. And now the C matrix is a little trickier. So the C matrix is what is our linear combination of the output? I mean, it's still the same thing, but you just have to watch out for feedback, okay? So looking from Y, we see that it's got B0 times, so we can't use this. We can't say X of n plus 1. We've got to find the combination of X1 and X2 at time n. We're not allowed to use n plus 1. You can do that, and you'll get interesting algorithms that way, but they're not standard state space. There are important algorithms that do that kind of trick. But that's a different subject. So what is it really? Well, you do see B0 times U. So you now found our D matrix, right? So there's a direct term, B0. So D is equal to B0. That just jumps out at us. But what about what is the function of the state variables? Well, we have to go through this summer and see that we've got the minus A1 here. And it also gets multiplied by B0 before it gets out. So X1 goes through minus A1 and then B0 before it hits the output. And so that's this term right here. And then this is the other thing to watch out for is that it can be used twice. So it got used once as a feedback and then secondly as a feed forward. So we actually have two terms here for the first output, which is B1, so we're talking about the coefficients of X1 making it to the output, which is, the first element of the C matrix. And so it's B1 times X1 plus B0 times minus A1 of X1. And so these are easy to accidentally overlook. You just have to be careful. And then it's the same story for the second state variable. It's B2 times that state variable plus minus A2 times B0 times that state variable, and we're out. Okay, so that's how you fill in the matrices by direct inspection, and that's all I've ever had to do. I've never had to do anything more fancy than that. But there are, fancy software systems for taking various canonical forms and cranking out these matrices. There's all sorts of tools out there. MATLAB probably has most of them. Okay, so let's look at a state space example for the biquad in Faust. Here we go. We will start out with just getting the biquad together. We pick a pole radius of 0.9, a pole angle corresponding to the sampling rate divided by 10. And this is the normalized radian frequency formula and the denominator coefficients of the transfer function, which go into the top row of the state space matrix. You've probably seen these expressions before. If you've worked with digital resonators, they come up all the time. And then this is the numerator. Just arbitrarily chose a 0 at DC and half the sampling rate. It's a very standard case for the biquad. You have a resonator with no response at DC or at infinity. Those are the zeros there. And so here's the direct form case, just straight out of filters.lib, TF2. And now here comes the state space case. And this is a very simple case with one input, one output, and two states, second order system. And so this is using pattern matching to set the coefficients. A11, A21, etc. So we have our denominator coefficients in the top row. This is one of the canonical forms for 2 by 2 states. Well, for a state space matrix, you have the denominator coefficients across a row. It can be the top row, it can be the bottom row, it can be the right column. There are various controller canonical forms, observer canonical form, all those canonical forms. And actually, I happen to have a page from MATLAB on canonical state space realizations. It's a good place to look. So there's companion canonical form, observable, controllable. And so, yeah, you can see that companion form has the denominator on the right. The companion matrix is the state transition matrix, the feedback matrix. And so the observer canonical form uses that companion matrix and defines the matrices like this. It's observable because it's got only one output. So you can't introduce zeros with only one output, but you can have zeros on input. So your inputs can encounter nulls going into the states. So you don't necessarily have controllability of all the modes, but you do have observability of all the modes. This is just a little by the way on state space stuff. And then there's controllable canonical form, where you have only one input coefficient. In other words, all this is the single input case, and all the input goes into only one state. It doesn't go to a bunch of states where you can induce zeros. But the flip side is your output is a linear combination of states, and you can introduce zeros, and there would be no observability at those frequencies. So you don't have guaranteed observability. So that's where the terminology comes from. And you can pick whatever form you want. But the form I'm going to talk about, well, we're going to get whatever form we get by just analyzing the block diagram. And it will turn out to be essentially the companion form with things flipped around. So the controllable canonical form has everything on the bottom, all the denominator coefficients of the transfer function. By the way, this is all continuous time. The discrete time case is similar. It's not that different. So we found it on the top row. So what we had was a controllable canonical form with a permutation. It's just like renumbering the states oppositely. So to just flip this up down, you would just renumber the states in the opposite order. So here we are just entering those numbers, and you can see that we are controllability canonical because we're feeding into one state. Can't introduce zeros that way, but the output could have a zero, so it's not necessarily observable. And then we have a feed around term. But we're just making a biquad using a state space model. We're not really concerned about it. Just intuitively, it's reasonable to know that your controllability and observability of a system have to do with whether or not there are zeros in the way. So if there's a zero canceling a mode in your system, then you can't control it, you can't observe it. And so you can see that it's different whether you're going in or coming out as to whether you have a 0 coming in or 0 coming out. Just a little by the way on state space. All right, so now this is the definition of the matrices, and we will, and remember we derive this directly from the block diagram. These are the matrix entries that we derived from the block diagram by inspection. And right now you also have to define, using in pattern matching you set a formula for different arguments. So so b of 1 comma 1 will get rewritten to 1, and you can have more rules for different cases. So b of 2 comma 1 gets rewritten to 0, and we're not writing anything else. Well, right now the Faust compiler requires you to have more than that, and so I'm just putting some arbitrary definitions for, but these rules follow the previous rules, so they are, lower priority. But if we didn't define any of these, then here's a catch-all definition, and that's presently required. That will probably go away. And then this is the definition of the matrix, and we've seen this before, and this is all the same. So that's just the same, general code for state space, and that's the Faust example. And so up here you can compare it. This is what I did to test it. I compared the direct to the state space and then differenced them and found that I got 0 to within machine precision. So for double, it's better than for single, and then for quad it's even better. And so that's always a good test. Okay, to conclude, we talked today about a number of physical modeling formulations, and here they are again. We're now the ones that are suitable for computer implementation are italicized, and these are the ones we talked about today in this workshop. So earlier we had talks on finite difference schemes, wave digital filters, and digital waveguides, and in my talk we saw some state space modeling and modal representations obtained by diagonalizing the state space model. And that covers quite a bit of ground, and hope you enjoy your models, and I look forward to hearing what they do.